Welcome back to Statistical Data Analysis 2. In this lecture, we are going to look at matrices. Why, you may ask? Well, because our goal next week will be to understand the so-called matrix formulation of the linear model, which is a very parsimonious and elegant, but at the same time general way to express any kind of linear model, including linear mixed models, with any number of predictors in it. And in order to get there, we need this fundamental concept from math, which is a matrix. Some of you may have worked with matrices in the past or know how to do basic operations on them, but maybe some of you don't. And that is basically what this lecture is for. Just a revision, or for some of you, introduction of what a matrix is mathematically and how we can operate on matrices. All right, so what is a matrix? Well, a matrix is basically nothing else than a rectangular array of numbers. For example, real numbers. And of course, such an array has a certain number of rows and also a certain number of columns. And so we could call a m times n matrix such an array which has m rows and n columns. That refers to the number of rows and to the number of columns. All right? So as an example, we could look at a 2 by 2 matrix. And a 2 by 2 matrix, as defined here, means it has 2 rows and 2 columns, right? So we can write it as follows. So we'll write an opening square bracket, which basically introduces that there is a matrix, and there will also be a closing square bracket on the other side. Or it could also be a normal bracket, depending on the notation, but this one is very typical. And so inside these brackets, we will now write the 4 values which are in our matrix. So it's a 2 by 2 matrix, that's why there are 4 values in it. And let's say our matrix contains the values 1, 2, 3, and 4. All right? That could be a possible 2 by 2 matrix, right? Now, I could define this matrix directly in R if I want to, okay? And that's what we're going to do now. So let's call this matrix M1 maybe. That's just going to be a variable name like any other. And so now I'm going to use the inbuilt matrix function, which is there to construct a matrix. And here's how it works. So the last 2 arguments will be the number of rows and columns of this matrix. In this case, if it's a 2 by 2 matrix, we'll have 2 rows and 2 columns. And the first argument is going to be a vector which contains the values that are going to go into this matrix. And if I give it the vector of integers from 1 to 4, then this will basically populate the matrix as given here. So it will start basically going down the first column, and then it will start going down the second column. All right, so it will do 1, 2, 3, 4. It will not do 1, 2, 3, 4, but it will really first go down a complete column and then go to the next column, right? And so if we do that, we can save this matrix as M1, and we can visualize what M1 is, and we see indeed this is what M1 looks like if we specify it as given here. Let's do the same thing again, but with slightly different values. So we're going to create a matrix M2, which is going to contain the values given in the following vector, the vector 2, 4, 6, 8. And again, we're going to have a matrix with 2 rows and 2 columns. So once we execute this command and print out what M2 is, we see this is our M2 now. So if I would write this, again, this would then look as follows. So this M2 matrix would be 2, 4, 6, and 8, closing bracket, right? And so these are 2 examples of 2 by 2 matrices. I could obviously have infinitely many more with different kinds of values in them. But obviously, we can also have matrices of other dimensions than 2 by 2. Let's see an example of a 3 by 2 matrix for a change, okay? So I could define a 3 by 2 matrix which I can give the name M3, and I will give it the following values, which will populate it, namely the values given in the vector 2, 4, 6, 8, 9, and 10. And then, as I said, I have to define the dimensions. So I run this, and this will give me the following 3 by 2 matrix, where as I can see, the number of rows is 3, there are 3 rows, and the number of columns is 2, there are 2 columns, okay? And likewise, I could also define a matrix, well, let's call it M4 then, which I will populate with the same values, only that now I will flip the dimensions. So now I will have a 2 by 3 matrix as opposed to a 3 by 2 matrix. And this will look as expected. So now I have, as we can see, 2 rows, but 3 columns. And again, the values have been put into this matrix in such a way that we first start filling out the first column, and then the second column, and then the third column. That's just how this matrix creation command works in R, okay? Let us now look at some basic operations that we can perform on matrices. One such operation, which just involves a single matrix, is the so-called transpose operation. The transpose basically says, give me a matrix of any dimensionality. Dimensionality means what is the number of rows and what's the number of columns. So if I know that, I know the dimensions of a matrix. 3 by 2 is the dimensions of a matrix, for example. And so I can give this transpose operation a matrix of any kind of dimensionality, and the transpose operation will basically flip the rows and columns. So what was rows before will become the columns of the matrix, and what was columns before becomes the rows of the matrix. Let me give you an example. Let's say we have a 2 by 3 matrix, which is the following. So 1, 2, 3, 4, 5, 6. And now if I transpose this matrix, let me just make this a little bit prettier. If I transpose this, it just means I get a new matrix, but while this one was a 2 by 3, the transposed one will now be a 3 by 2, where what was in my first column originally is now in my first row. And what was in my second column before is now in my second row. And so on, okay? So this is going to be the result. It just basically takes the matrix and just flips what had been the rows into columns and the columns into rows, all right? In R, we can accomplish this operation using the T function, right? T as in transpose. So if you recall, we had defined this matrix M1, for example, which was the matrix 1, 2, 3, 4, 2 rows, 2 columns. And if I compute the transpose of that matrix, I will get a new matrix, which, well, in this case is also of 2 by 2 dimensions. But crucially here, what was the first column before is now the first row, right? And what was the second column before is now the second row. Or let us look again at matrix number 4, which was a 2 by 3 matrix. If I transpose that one, I will get the following result, which is now a 3 by 2 matrix, similar to the example here on the left side, right? So that's the whole idea behind the transpose. It can be applied to any kind of matrix. It really doesn't do any big magic. It literally just turns the rows into columns and the columns into rows, right? So an M times N matrix will have a transpose, which is a N times M matrix, okay? Another basic operation on matrices is matrix addition and matrix subtraction. These are also very easy to grasp because they work in a quite simple way. The only thing to consider here, of course, is when we are adding or subtracting stuff, we are always doing this in relation to 2 objects, okay? So in this case, 2 matrices. Let's say we have a matrix which has the values, 1, 0, -2, and 4. That's a 2 by 2 matrix, of course. And I can add to that matrix another matrix which has the values 1, 2, 3, and 0, maybe. And the result of this addition will literally be just taking the value that is in the upper left corner, so like the first row, first column value of the first matrix, and finding the corresponding value of the second matrix, and then doing this element-wise addition. So, and then in the resulting matrix, so this was a 2 by 2, and this one's also a 2 by 2, and the result of this addition will also be a 2 by 2 matrix. That's characteristic of matrix addition and subtraction, that we need two matrices with the same dimensions, and the result will again be a matrix of the same dimensions. And so, as you might have guessed already, we will do 1 plus 1, which gives us 2. We will do 0 plus 2, which also gives us 2. We will do minus 2 plus 3, which will give us 1. And we'll do 4 plus 0, which will give us 4. So that is going to be the result of this addition. Okay? Likewise, I could do matrix subtraction, which is really just the same thing, just not adding numbers, but subtracting the second matrix from the first one, and doing that element-wise with the values that are inside that matrix. So if I'm going to do subtraction on these two matrices, I'll have 1 minus 1, which gives me 0. I'll have 0 minus 2, which will give me minus 2. Minus 2 minus 3 is going to give me minus 5. And finally, 4 minus 0 is still going to be 4, okay? So that would be the result of matrix subtraction on this particular example. We can also see this in R again. Recall what our matrices M1 and M2 were. These were of the same dimensions. Both were 2 by 2, so it's fine. We can add or subtract them. And let's see what happens if we add them. Well, if we add them, we get a matrix that's literally an element-wise addition, for example, of this first element in the first row and first column and this one, just as we saw here on the left side. We could also do matrix subtraction. So we'll subtract maybe subtract M1 from M2. And so in this case, we get 1, 2, 3, 4, which coincidentally is the same as M1, because M2 is just basically taking the numbers of M1 and taking them by 2. So once we subtract that once from M1, we will again get a matrix that's actually identical to M1. We can also do a small sanity check. If we do M1 minus M1, for example, what matrix should we get? Maybe think about it for a moment. All right, so it's a matrix, 2 by 2 matrix, all full of zeros, because we've subtracted M1 from itself, which means we did element-wise, we subtracted the element from itself, and whatever the original number was, the result is going to give us 0, right? So that is how we can do matrix addition and subtraction in R. We can use the plus and minus commands in the same way. Oops, the plus and minus commands, there they are, in the same way that we would also use them on numbers in R, for example. Now, it should be noted that really it is essential for matrix addition to work that we have the same dimensionality on both matrices. That applies to both addition and subtraction, okay? And if we don't, then the result is just undefined. So we can't add a 2 by 3 matrix, let's say, to a 2 by 2 matrix. It's just not possible. The addition is not defined. We can also see this in R. If we tried, for example, to take M1 and then take M3, which was, so M1 was a 2 by 2 and M3 was a 3 by 2. If we try to add them, just because we really want to, we would see that there's an error, right? So the error says non-conformable arrays, which basically translates to these matrices have different dimensions, so I just can't add them together. And likewise, subtraction will also fail in this case. However, there is in fact an operation that we can apply in relation to M1 and M3 together. It is not addition or subtraction, but it is matrix multiplication. And we're going to do this the other way around now. So we're going to first see the result in R and then try to understand step by step how this operation works, because that one is a little bit more tricky than addition or subtraction. So let's first do it in R. In R, we can multiply two matrices using this special operator, which is basically percentage sign, asterisk, another percentage sign, and then the name of the other matrix. And in this case, I'm going to do M3 multiplied with M1. I'm doing a conscious choice to write m through multiplied m1 and not the other way around. We're going to see why, okay? But here this is important. And I'm going to do this. So what is m3 times m1? Well, it turns out that it is actually this new 3x2 matrix with these somewhat mysterious entries of 18, 22, 26, 38, 48, 58. So these somehow came about from these two original matrices, but it's a bit less obvious compared to addition and subtraction of how to actually do this and which kind of matrices can be multiplied. So as we saw before, we couldn't do m1 plus m3. We also couldn't do m3 plus m1 either, but we can do m3 multiplied with m1. And what does this mean? Like, why can we do this, and how does this multiplication operation work? That is what we're going to see next. In order to understand matrix multiplication, it is useful to maybe take a step back and first think about something else, which is the dot product between two vectors. Maybe you remember from high school how to compute such a product between two vectors. But we will see in a moment that this is actually very related to what is going on when we do matrix multiplication. So the dot product between two vectors. Let's focus on this for a moment and we'll get back to our actual topic, matrix multiplication, in a moment, once we understand this. So this is our small step back here. So suppose you have two vectors. One vector, let's call it u maybe, which contains the values 1, 3, 2, 1, and 5, right? Maybe you've seen vectors written differently, so sometimes you would also write such a vector like this, 1, 3, 2, 1, 5. Okay, that's just a different way of writing it. The important thing is that a vector is a one-dimensional array of numbers, so kind of like a step back from a matrix, which is two-dimensional. A vector is just one-dimensional, okay? So let's say this is our first vector, and because we want to do a dot product, we need another one. So let's say we have another vector which is v, and v is going to be the vector that contains the numbers, let's say 2, 6, 8, 9, and 4. All right? Notice that both of these vectors are of the same length, and we can call this length n maybe. And so the length is 5 because, well, each of them contains exactly 5 elements, 5 numbers. Okay? Now with this we can define the dot product between these two vectors as u dot v. That's why it's called the dot product, because we write this dot operator here. And that's going to be just the sum of taking the simple product between the first element of u and the first element of v. So it's going to be u1 times v1 plus u2 times v2 plus, and that goes on up until the last element of each vector, which will be at un vn. In our case, that's going to be at 5, okay? But more generally speaking, we can write it like this. All right, so in this case, we could compute this concretely as, well, that's going to be 1 times 2 plus 3 times 6 plus 2 times 8 plus 1 times 9 plus 5 times 4. And if we evaluate this, this will give us a particular number. We can obviously quickly finish this calculation by hand, but we can even quicker do this in R. Well, here I've already defined these vectors u and v, and I'm just going to say, okay, what is u times v? That's just going to give me the element-wise multiplications, like this one and this one and this one and this one and this one, but separately in a new vector. So the only thing that's left to do is to take the sum of this result, and this will give me the result of this operation, which in this case will be 65 overall. Okay? So in summary, this 65 is the dot product between the two vectors u and v as given here. Another thing I can do, obviously, is also take the vector u and then again the vector u, like take the dot product between a vector and itself, right? That is obviously possible because if I take the vector itself, this condition that they have the same length will be satisfied trivially. So I can also just take the dot product of u and u, that would be 40 in this case, or I could do the same thing for v and itself. So I'm going to take the dot product between v, and this would give me 201. All right, so the dot product in summary is always a number, and this number comes about as the sum of the individual element-wise products between two vectors. By the way, an interesting property of the dot product, which is worth mentioning here, is that if we have two vectors u and v, and we see that their dot product is 0, that means, that is basically the case if and only if u and v are orthogonal to each other. Orthogonal means they are situated in 90 degrees angle to each other, okay? And so how do arrays of numbers situate themselves orthogonally to each other? Well, you just have to visualize the vector in a coordinate system. For example, let's take two-dimensional vectors because that makes it much easier conceptually. Let's say we have a coordinate system with 2 dimensions. Okay, so that's one dimension and that's the other dimension. And in this coordinate system, we will have two vectors. For example, this is one of them. This is vector A, and then we have this vector, which is vector B. Okay, and so the specific values of these vectors in this case could be maybe 1, 1, and this vector B could be, let's say, 1, -1. And what this tells us is that, okay, if we can see here geometrically that the angle between these two vectors is a right angle, that is a 90-degree angle, then, okay, that's just another way of saying they're orthogonal to each other. So given this property and given that we know that they're orthogonal to each other, we could now confidently say that the dot product between them has to be 0. We can check this for this particular example, if that's indeed the case or if I'm just making stuff up. Let's say we have the vector 1, 1, and its dot product with the vector 1, -1. Now, according to the definition of the dot product, this will be 1 times 1 plus 1 times -1. And that is just 1 minus 1, aka 0, right? So this is indeed the case here. So we can show mathematically, given this relationship between the dot product and the orthogonality, that once we've seen that the dot product is indeed 0, we also know that the angle has to be a 90-degree angle. That is the angle between the two vectors of which I've taken the dot product. Okay, but back to our goal of understanding how this all relates to matrix multiplication. Let's take our two vectors, u and v, but let's convert them to matrices, okay? And so we're going to convert u into the following matrix, namely into the matrix 1, 3, 2, 1, 5, expressed in a single row. And we're going to take v, but we're going to transform it into a matrix in a slightly different way. Namely, we're going to transform it into the matrix 2, 6, 8, 9, 4, but expressed in a single column, not a single row, okay? So here we have, as you can see, a row with, a matrix with 1 row and 5 columns, 1, 2, 3, 4, 5. But here we have a matrix with actually 5 rows, but only 1 column, okay? And these two matrices can be multiplied together. The general idea is that if I have a m times n matrix, and then I want to multiply that with a n times p matrix, that will work, okay? That will give me a result, which is a matrix that has the dimensions m times p, okay? And the crucial thing is that this m times n matrix is on the left side of the multiplication, the n times p matrix is on the right side, and the result, is the result of the operation. So in other words, the only thing that has to be matched between the two matrices that are multiplied is the number of columns of the first one, which has to be the same as the number of rows of the second one, okay? So on the left side, I need to have the same number of columns as I have number of rows on the right side, which is satisfied here, because here we would have m times n, where n is 5, and n times p, where n is 5 again, so that will work. And this will give us as a result a m times p matrix, where m is 1 and p is also 1. And now here comes the crucial connection to the dot product, which is that this 1 times 1 matrix I will get by multiplying these together will contain as its single value exactly the dot product of these two vectors, namely 65. So just writing this out explicitly, we could say that the matrix multiplication, let me make this a little bit smaller. If we do 1, 3, 2, 1, 5, multiplied with 2, 6, 8, 9, and 4, then this will give us as a result the matrix with just a single row and a single column that contains exactly this value. Which is the case because, well, the idea if we have a 1 by n and an n by 1 matrix is that we can just think of it as the dot product between two vectors. One vector represented as a row and the other vector represented as a column, and we will multiply the first element of this vector with the first element of that one, this one with that one, this one with that one, and so on, okay? But the crucial thing is really on the left side we need to have this row vector, and on the right side we need to have this column vector. Only in that case will the multiplication work. So the multiplication doesn't work once we flip those around. It really has to be in this particular order, that the number of columns of the left one, namely 5 in this case, is the same as the number of rows of the second one, namely 5 again. And the result will be m times p, that is 1 times 1. And the single element here in this case will just be the dot product, okay? All right, now we've seen the simple case where m is 1 and p is 1 when matrix multiplication is basically equivalent to computing exactly one dot product. But now let's do a small modification here. So I'm going to delete this result again. And now let's say we are interested in multiplying this matrix, which, as we said, is a 1 by 5 matrix, with the following matrix, where here it comes. We will have the, oops, let me take the other pencil, where we have the following entries here as a second column, namely 1, 3, 2, 1, and 5, okay? So you might recognize these numbers. Well, they're actually just, again, a repetition of the entry of the u vector here. But now it's just as part of a matrix as the second column of the matrix. So to write down the dimensions here, we can say this one is 1 times 5, and this one is 5 times 2. So this will work because, again, the number of columns on the left side is matching the number of rows on the right side, so that's fine. We'll get a result. And our result will be, according to this rule, a matrix of the dimensions 1 times 2, right? Because that was our m and p in this case. So as a result, we expect a 1 times 2 matrix. And indeed, if we compute this multiplication, what we will get is first the dot product of this vector and that vector. Okay, so we'll do 1 times 2 times 3 plus 3 times 6 plus 2 times 8 and so on, which, as we saw here, was 65. And then we will have another cell here, so 1 row but 2 columns, and in the second cell we'll have the dot product of this vector, of this row vector with that column vector. which is like the dot product of U with itself, which, as we saw earlier in R, would give us a result of 40, okay? So this is basically a compact expression of computing two dot products at the same time. So once the dot product of U with V, which gave us 65, and also the dot product of U with, again, U itself, which gave us 40. And as we saw, well, we already extended the number of columns on the right side of the multiplication. We can also do the same thing to the number of rows on the left side of the multiplication. So let's say I'm deleting this result again, and we're going to say we will have, well, kind of the same matrix, but we will add another row on top. In this case, let's maybe just, for simplicity, have a row that's just full of ones. So it's going to be row 1, 1, 1, 1, and 1, okay? And what does that mean now? So that means, kind of an analogy, that here now we have increased the number of rows, obviously, to 2. So the new dimensions of this matrix on the left side will be 2 times 5. And if we now think about the result that we expect for this operation, according to this general rule, it should be again of dimensions m times p, where here m is 2 and p is 2, so the result should be a 2 by 2 matrix. Now, how can I find the values of this 2 by 2 matrix? Well, below, so okay, let me write first the brackets, and I will have to put 4 values in. In the second row, like in the row below, we will have the same result as we just saw when we didn't have this new row on top. So it will just be 65 and 40. And now we are basically doing the same thing, but regarding now the new row, which is on top. So that's why there is also a new row on top in the result, in addition to what we saw earlier. So now we will have to take this vector 1, 1, 1, 1, 1, 1, and take its dot product with this first column vector. So that will be 1 times 2 plus 1 times 6 plus 1 times 8. So basically just 2 plus 6, which is 8, plus 8, which is 16, plus 9, which is 25, plus 4, which is 29. Okay, so that will be our value here. And now in this last missing cell, we will have to take the dot product of this row vector on the left with this second column vector on the right. So it will be 1 times 1 plus 1 times 3, so in short just 1 plus 3 plus 2, which is 6, plus 1, which is 7, plus 5, which is 12, okay? So this will give us the value that we'll have to put in here. So as you can see, matrix multiplication is basically just computing a series of dot products in according to a particular set of rules, which states that on the left side, the matrix on the left side of the multiplication basically represents a collection of vectors represented as rows, okay? And the right side of the multiplication represents a series of vectors which is given as columns, okay? And we will have to take the dot product of each row vector on the left side with each column vector on the right side. And we'll have to fill this resulting matrix here accordingly. And just to really understand which dot product goes into which cell here, well, basically, if we are in the uppermost leftmost cell of the result matrix, this is basically saying I want the very first row vector, maybe like this, the very first row vector on the left side multiplied as a dot product with the very first column vector on the right side, okay? And this dot product will give me this 29 as a result here. If I go one cell to the right, I'm saying, okay, now I moved one column to the right, so now I want the second column vector on the right side, but still the first row vector on the left side. And these two together will give me this 12 as a result. Likewise, if I'm here in the second row and first column of the result matrix, I'm basically saying I want the second row vector from the left side of the multiplication with the first column vector from the right side of the multiplication, and their dot product will give me the 65. And finally, if I'm in the second row and second column of the result, I'm basically asking for the second row vector on the left and the second column vector on the right to be multiplied together as a dot product, and that will give me this 40 as a result. That's basically all that matrix multiplication really is mechanistically. So we're just taking some dot products kind of compactly represented as matrices, as rows on the left side and as columns on the right side, so the vectors basically that go into the dot product operation, and then we store the result of each of these dot products in this resulting matrix, which has the dimensions as specified here above. Okay, so now we basically understand how matrix multiplication works based on this idea of the dot product. We can also very smoothly and quickly run matrix multiplication in R, as we saw already with one example, which previously looked a bit mysterious. So maybe let's first revisit this example and see how it all makes sense now with this clarification in mind. As you remember, we had previously seen the multiplication of this matrix, which we called M3, which was a 3x2 matrix, with that matrix M1, which was a 2x2, and it gave us this result here. And now let's maybe unpack and verify that this result actually makes sense. Okay, so first sanity check, M3 is a 3x2, so n is 2, and M1 is a 2x2, so n is again 2, so the two n's match, and that means that we can, in principle, do the multiplication. And also, the resulting matrix should be m times p. Recall that m was 3 and p was 2. So as a result, we expect a 3x2 matrix, and indeed we have a 3x2 matrix as a result here. So what R gives us as a result from the dimensions at least already looks very plausible. Now let's also maybe quickly do this by hand to verify if we'll get to the same numbers. So what this means is, okay, on the left side we have the matrix 2, 4, 6, and on the right side we have the second column, which is 8, 9, 10, so that's the entire matrix basically. And we multiply this with a 2x2, which is 1, 2, 3, 4. And we know from this rule of how the dimensions work for matrix products that the result has to be a 3x2 matrix as well. Okay, so this will be a 3x2. And in this very first cell, we'll have to take what exactly? Well, we'll have to take the first row on the left with the first column on the right. So 2 times 1, which is 2, plus 8 times 2, which is 16. Okay, so 2 plus 16, overall, this gives us 18. Likewise, when we are here in this second column, but first row of the result matrix, we'll have to take the second column on the right and the first row on the left. Okay, so we will do 2 times 3, which is 6, plus 8 times 4, which is 32. So 6 plus 32 gives us 38. All right, so that already looks very plausible. It matches what R gave us. And believe it or not, if we would do the same thing again for the remaining rows and columns, of which we will have to take the respective dot product, so always take rows from the left and columns from the right, and arrange them here accordingly, then we will get indeed this matrix, which we also saw in the R output with the following values: 22, 26, 48, and 58, given as follows. So that's the whole mystery behind this output in R. It's basically just doing what we just learned about how matrix multiplication works. Now, you can also see some counterexamples. So if this condition is violated, that n and n are equal, so that basically the number of columns on the left and the number of rows on the right is equal. If that's not the case, then we will get an error message. So we can indeed see that in R if we have to maybe arrange this window a little bit here. So if we take M1 and want to multiply this with M3 this way around, we should get an error. Why? Because M1 is a 2x2, so n would be 2. But M3 is a 3x2, so n would be 3. So you can't have n equals to 2 on one side, but n equals to 3 on the other. That will give us an error. And as expected, we get this usual error in R here, which complains about dimensions of matrices not matching up for the particular operation we want to apply, right? One thing we can do though is if we remember, okay, M1 was this, and we also had a matrix M4 specified, which was a 2 by 3. So if we now do M1 times M4, that should work, because we have a 2 by 2 on the left, so n is 2, and a 2 by 3 on the right, so n is again 2. So the number of columns on the left matches the number of rows on the right. Both are 2, and that will give us a sensible result as well. There will be no error message, right? That is how we can multiply two matrices in R, given that this condition is true. There's also another kind of multiplication which applies to matrices, which is called scalar multiplication. Now that one is much simpler, and as opposed to matrix multiplication, this doesn't apply to two matrices, but it applies to a matrix on the one hand and a number, like a scalar, on the other hand. For example, we could have 5 as a scalar, and if we multiply this with the matrix 1, minus 1, 0, 2, then the result will just be each element of this matrix multiplied with 5, with the same dimensions as we had before. So the result will still be a 2 by 2, but now instead of 1 we will have 1 times 5, so 5 here. Instead of minus 1 we'll have minus 5, and here 0 stays the same, and 2 times 5 is 10. So that is the whole idea behind scalar multiplication, is take a matrix, multiply it with a number, which could be some real number, whatever, for example 5, and then each element of this matrix will just be scaled, like multiplied with this by this number, okay? And it's also, we can write it either way. We could write it like this, or we could write first the matrix, then the scalar. So in this case, we would have this scalar on the right, and then left next to it we could have the matrix that will be exactly equivalent. So in this case, again, I would just write 1, minus 1, 0, and 2. So as opposed to matrix multiplication, where the order matters, where the order literally can decide between operation possible or not possible, due to this situation here, the order is completely irrelevant for scalar multiplication. We can just write the scalar to the left or to the right. That really is just all the same here. Let's see some scalar multiplication in action in R maybe. So scalar multiplication as an example, what could be our scalar? Maybe minus 2. And we want to multiply minus 2 with the matrix M4, okay? So that will give us a new matrix, which will be the same as M4, only that each element has been scaled by minus 2. So a 2 has become a minus 4, a 4 has become a minus 8, and so on. That is our result of the scalar multiplication. And as we saw here, it really doesn't matter if this minus 2 is on the left or on the right side. We'll write it like this, and the result will be the same. Also note, the operator in R for the scalar multiplication is just the normal asterisk without any percentage signs, like just the simple asterisk that we also use if we want to multiply two numbers, let's say 2 times 3, okay? It's the same symbol if we want to do scalar multiplication. For matrix multiplication, we have to use this special operator instead, which is the percentage asterisk percentage sign. All right, so this concludes the explanation of multiplication on matrices. We've seen matrix multiplication and how this can be broken down or thought of as basically a series of dot products on vectors. And we also saw scalar multiplication, which is just a matrix scaled by some number, where we will apply this multiplication to every element in that matrix, as seen here. All right, so as the next topic, we are going to look at special kinds of matrices, namely diagonal matrices and identity matrices. A diagonal matrix is, as it is said, a special class, like a special kind of matrix. Okay, not every matrix is a diagonal matrix, but every diagonal matrix is obviously a matrix, right? It's a subset of the possible matrices that there are. And in particular, it has to satisfy certain criteria. And the criteria are, for once, that it is a n times n matrix. In other words, it's a square matrix, like it has the same number of columns as it has the number of rows, okay? And the second criterion is that, well, if we think of this matrix as this square, we can think of the diagonal that goes from the upper left corner to the lower right corner, regardless of whether this is a 2 by 2 or a 3 by 3 or 100 by 100. There is like values that are exactly on the diagonal, where like they are on the third row and the third column, for example, or on the 50th row and 50th column, or on the first row and first column. Like these are values which are on the diagonal. It's just about this diagonal, not that one, okay? It's just about the diagonal where the row number matches the column number. And so basically the second criterion says that all values in this matrix which are not on this diagonal, like which are not on that diagonal, this one, all of those will be equal to 0, are equal to 0. So what is an example? Well, we can imagine a simple 2 by 2 matrix. So let's start with examples here, and we could have, let's say, 2, 0, minus 3, 0. That's a diagonal matrix because, well, the diagonal values can be whatever, but these two values which are not on this diagonal are 0. So that's a fine example. Another one could be, let's say, 1, 0, minus 4, 0, 0, 0, 0, 0, and 0. It's a 3 by 3 matrix. Now, obviously, the zeros are not only on the cells which are not on the diagonal, but we also have a 0 here, but that's fine, right? So this criterion says we have to have zeros everywhere where it's not the diagonal. We can have zeros on the diagonal as well. That's possible. It's just not required, okay? So this is a correct example too. Or we could have, let's say, a 4 by 4 with the following values: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1 finally. Now this one's a bit boring, it just has ones on the diagonal, but that's all fine because the criterion says we need to have zeros everywhere else, and that's satisfied here too. So just the diagonal has different values, ones in this case, but everything else is 0, so this counts as a diagonal matrix as well. So the diagonal matrices are already a special kind of matrix, but what if I told you that there is an even more special kind of matrix, which is a subclass of the diagonal matrices? That's what we refer to as identity matrices. Or if we are just speaking about one dimensionality, it will be the identity matrix. Like there's only a single one of them for a specific dimension. The identity matrix is basically defined as, well, diagonal matrix, but with another criterion. So we will have to say all values which are not on the diagonal are 0, yes, but also, like as the third criterion, all values on the diagonal have to be equal to 1. So all values on the diagonal are equal to 1. So from the examples on the right here, which ones satisfy this? Like which of these diagonal matrices are also identity matrices? Well, actually only this one, right? Because here we indeed have 1, 1, 1, and 1. But for those we have also other values on the diagonal. So this one is not an identity matrix, and neither is this one. This one here, in particular, is also called the identity matrix, like it's sometimes written as I for the fourth dimension, because here we are speaking about the case where we have 4 rows and 4 columns. Okay, and likewise we could also have the identity matrix for 2 dimensions, which would be 1, 0, 0, 1, or the identity matrix for 3 dimensions, which would be, as you might guess, 1, 1, 1 on the diagonals and everything else being set to 0. An interesting property of the identity matrix at dimension n is that if we take this identity matrix, so I subscript n, which obviously has the dimensions n times n, it's a square matrix, and then we multiply it with any other matrix which has the number of rows as n and then number of columns as something else, let's say, then this will be exactly equal to this matrix A again. So under matrix multiplication, if we multiply something with the identity matrix, it will stay the same. It's like multiplying a number to 1, like it doesn't change the result. And this is like multiplication from the left side. We also can state a similar property for multiplication from the right side. So if we have the identity matrix on the right side, then this obviously will again have the dimensions n times n. And on the left we have A, which in this case would be required to have the dimensions some m times n, so just the number of columns of A has to be the same as the dimension of the identity matrix. And also in this case, the result would stay exactly A. So whether we multiply, whenever we are allowed to, of course, but whenever we are allowed to, we can multiply the identity matrix with some other matrix, either from the right or from the left. As a result, we will always get this same other matrix back. Okay, so that's the key property of what the identity matrix does. It literally leaves like the other matrix, which is part of the multiplication, unaffected. It will be exactly that same matrix again in the result. In R, the general command to generate a diagonal matrix is the diag command, which I will just give some vector, for example, the vector 1, 2, 4, which represents the values that will be on the diagonal. So this is like working for any kind of diagonal matrix. So this will give me the diagonal matrix with the values 1 to 4 on the diagonals. But now obviously we want to see identity matrices in particular. So here we will just use the diag command all the same, and we will provide a vector of just ones, okay? And what's like an efficient way to generate a vector of just ones for any number of like repetitions? We can use the rep command, and as a first argument we will give it 1, which represents the value that it should be generated over and over again, and as the second argument we will give it the number of times that we want to generate this value. So we want 3 ones in a row, so like a vector with 3 elements, 1, 1, and 1. And this will be our input into this diag function, which will create a diagonal matrix accordingly. So this will now generate us literally the I3 identity matrix, the identity matrix for the dimension 3, right? Just has ones on the diagonal and zeros everywhere else. Likewise, we can generate the identity matrix for the second dimension. So this will just be 2 rows and 2 columns. Again, the diagonal is all ones and the off-diagonal values are all 0. And maybe we can save this even in a variable, call it I2. And just to see this property in action, well, we can maybe take our matrix M1, which was this particular 2x2 matrix. If we do I2 matrix multiplied with M1, then, so recall M1 was 1, 2, 3, 4. As a result, we'll get exactly the same, 1, 2, 3, 4, confirming this property that the identity matrix is basically multiplying with the identity matrix will preserve whatever the other matrix was. And we can also see this for multiplication from the right side with the identity matrix. So we can also do, because it's a 2x2, so all dimensions, rows and columns are 2, so we can do I2 times M1 or M1 times I2 in this case. So let's try the second option, and we'll write M1 matrix multiplied with I2. And that also gives us the same result. So 1, 2, 3, 4, which is just what the original M1 was in the first place. As another example, consider the matrix M4. That was a 2 by 3 matrix. So here we could apply the I2 matrix from the left side and multiply it with M4, because the number of rows of M4 has to be equal to the dimension of the identity matrix, which is 2. So we can do that and it will just stay all the same. Or we could do, well, we'll have to define I3 first. So I3 will be diagonal of, let me just write it in a simple way, 1, 1, 1. Okay, that's my I3. You can see it here. And if I do M4 matrix multiplied with I3, this would be this case here, where the number of columns of my matrix, which is interesting, the M4 matrix in this case, is the same as the dimensionality of the identity matrix if I have the identity matrix on the right side of the multiplication. So this should work too, and again it should just give me the original M4 matrix as a result again, just unmodified. Okay, so that is how we can do multiplication of the identity matrix either to the left or to the right, be it for square matrices like M1, but also for any other kind of matrix like M4, which happened to be a 2 by 3 as we defined it here in this R session. The next concept we want to introduce here is the power of a matrix. The power of a matrix is something that can be computed specifically and only from square matrices. So if we have a square matrix, which means a matrix with the same number of rows as it has the number of columns, then we can, so let's call this matrix A, for example, then we can, of course, compute the multiplication, the matrix multiplication of this matrix with itself. So we could say A times A as a matrix multiplication. It's possible because the number of rows and number of columns are all the same for a square matrix. And we could also write this, just as we would do for numbers, as A to the power of 2, okay? Or if we were to do the matrix multiplication of A, and then that multiplied by A again as another matrix multiplication, then this would be A to the power of 3, and so on. So we could do this for any repetition of multiplications that we like, and the result will then be A to the power of some number n, which describes the number of times we have multiplied the matrix with itself. Now, we can do this only for square matrices, obviously, because otherwise the multiplication condition wouldn't match up, that the number of columns from the left one has to be the same as the number of rows from the right one. So that's a constraint. And recall that some interesting square matrices that we saw were the diagonal matrices. So there's this interesting case, maybe I'll write it in this bubble here. So interesting case and easy for computation is the diagonal matrix, and by extension obviously also the identity matrix, where it's really trivial. Because for a diagonal matrix, this multiplication, repeatedly applying this multiplication, amounts to just taking the power of the numbers that are in the diagonal. Okay, so if I take, for example, the diagonal matrix 1, 2, 3, and which is 0 in all other cells which are not on the diagonal, and let's say I would want to take the second power of this, so this matrix to the power of 2, you could say, then this is actually the same only for the diagonal matrices. This simple rule applies of taking the power of each of the diagonal values. I could do 1 squared, 2 squared, and 3 squared, and everything else still stays at 0. And now this will be, of course, I mean, you can all do the math. It will be 1, 4, and 9 on the diagonal, while everything else stays 0, right? And even more trivially, for for the identity matrix, maybe I'll write it here like as another even more special case of the special case. So identity matrices, there it really doesn't matter how often you take the power because it will always stay the same, right? So for an identity matrix, you can do whatever power you like I to the power of n, whatever, and this will still be equal to I. For example, if we had the second dimension identity matrix, which is 1, 1, 0, 0, that to the power of 35 will still just be equal to the same thing, namely 1, 1, 0, 0, like the same identity matrix I2, okay? So this is the power of a matrix. It can be computed for any kind of square matrix, but as we saw here, it is particularly easy to compute for diagonal matrices. And it is totally trivial for identity matrices where it doesn't change the matrix at all. All right, so we have these concepts all clear now, I hope. Now let's talk about the next thing, which is the inverse of a matrix. So for the inverse of a matrix, again, we have to exclusively think about square matrices now. That's the only kinds of matrices where this might work. It will work for some, but not all of them. And in particular, we will have to imagine that we have two square matrices. Let's call them A and B maybe. So these will be of some dimension or order n times n, okay? Could be both 2 by 2, could be both 3 by 3. Important is they have the same dimensions, okay? Now, if the following equality holds, namely the equality that multiplying A times B this way, A into B, if that is equal to multiplying B into A, and that is equal to the identity matrix of the particular dimension we are in that case, we can say that B is the inverse of A. So if that is the case, then B is the inverse of matrix A and vice versa. And we can also write the inverse as follows. So we can write B is equal to A, and then we write this, which looks like to the power of -1, which is our notation for inverse, okay? So B is equal to A to the power of -1. That just reads as the inverse of A. So B is equal to the inverse of A, right? And likewise, the vice versa case, we can say that A is the inverse of B. So put differently, we can say now that when we have a matrix A, whatever it is, it has to be a square matrix, of course, and we multiply it by its inverse, then we will get the identity matrix as a result, okay? That's the key property that defines the inverse of a matrix. And this also works the other way around. So A inverse multiplied with A will also be equal to the identity matrix. So that's the property that has to hold. Now the interesting question is, of course, how can we find an inverse for a square matrix that is given? And is this always possible? So answer to the second question, it's not always possible. And in fact, we can distinguish square matrices into a certain class of matrices which are invertible and others which are not. And answer to the first question, well, there are different methods to it, to do it by hand. Conveniently for us, we don't have to delve into the details of them because we can use R to automatically find an inverse if there is one. So let us look at how we can find an inverse for a given square matrix if there is one, using a simple built-in R function. All right, so let's maybe define a matrix A, which could have maybe 2 rows and 2 columns, which makes it a square matrix, and as the values, we'll give it the values, maybe the values of 1 to 4, right? And now we can use the function solve in R in order to find the inverse of A. So once we apply this, we will get as a result the inverse of that function A. And so just that you believe me that it's indeed the inverse, we can make this sanity check. So if we take A and then matrix multiplied with inverse of A, this will give us the identity matrix, as you can see. And also, if we do it the other way around, we should get the identity matrix again. So that seemed to work. Now let's consider a different matrix. I'll call it maybe matrix C, okay? And this matrix will have the values, so will again be 2 by 2, and it will have the following values, namely the values 1, 2, 2, and 4, okay? That is my matrix C, you can see it here, and let's try to find its inverse. If we type solve C, we can now see an error, right? Why? Because this particular 2 by 2 matrix does not have an inverse. So as you see, we can, as I already hinted at, there are invertible matrices. For example, our matrix A that we just had here in the R session. But there also are matrices that are non-invertible. And another way of saying this, like 2 synonyms for this, is that non-invertible matrices are also called singular matrices, and likewise invertible matrices are also called non-singular matrices. So that is like slightly confusing double terminology, but just keep that in mind. So whenever you see invertible, it basically means non-singular, and when you see non-invertible, it basically means singular matrix. So we just saw in R, we saw 2 examples. One was an invertible matrix and the other wasn't. So here we had an example of an invertible matrix, namely the matrix 1, 2, 3, and 4, for which we could indeed find an inverse. So that inverse of that was what R gave us further above here, namely the 2 by 2 matrix -2, 1, 1.5, and -0.5. But then we also had an example for a matrix which could not be inverted, namely the matrix 1, 2, 2, 4. So that was an example for a non-invertible, aka singular matrix. And as we saw, this matrix could really not be inverted. So if we try to do this, this resulted in an error, okay? So this means that the inverse is not defined, basically. And the interesting question you might be asking yourself is why? Why are these 2 different? Why can we find an inverse for the matrix 1, 2, 3, 4, but why couldn't we find one for the matrix 1, 2, 2, 4? Okay? Now let me explain why that is. So to understand this, we will have to introduce the concept of linear independence. So linear independence means that when we look at a matrix and like its rows in particular, we would say that the rows of a matrix are linearly independent from each other. So for example, the rows, that would be row 1 and that would be row 2. So row 1 is this and row 2 is this. Or likewise for that example, row 1 is 1, 2 and row 2 is 2, 4. If there are no values alpha and beta whatsoever, which are not 0, which make the following equation true, so which satisfy that alpha times row 1 as a vector plus beta times row 2 as a vector is equal to the 0 vector, which in this case is just the vector 0, 0 for 2 dimensions. Like if we can't find any such coefficients, which are not 0 themselves, obviously we can always put alpha equals 0 and beta equals 0, and this will make the equation true. But if we cannot find any other pair of alpha and beta values which make this true, then we can say that these rows 1 and 2 are linearly independent of each other. So row 1 and row 2 are linearly independent. Okay? Now, the contrary case quite easily follows from that, right? So if I can in fact find some value alpha and beta, which makes this equation true, where alpha and beta are not 0, if I can find it, then I would speak of row 1 and row 2 as linearly dependent. Okay, not linearly independent, but linearly dependent in this case. And the idea is that if the rows of a matrix are in fact linearly independent of each other, in that case, the matrix is invertible, is non-singular. Then we are in this case here. But if I see that the rows of a matrix are linearly dependent with respect to each other, then we speak of a matrix that is not invertible, aka that is singular. And let me just show you for this example why here we can in fact find two values alpha and beta which make this equation true. So we could, for example, write that alpha is equal to 2 and beta is equal to -1. Well, in that case, let's see what this equation gives us. So it will be alpha, so 2 times row 1, 1, 2 as a vector, plus -1 times row 2, that will be 2, 4. And so this will be equal to 2, 4 minus 2, 4, and that is in fact equal to 0. So the fact that we did find values for alpha and beta, which make this equation true, which are not equal to 0, they are in fact 2 and -1, this leads us to conclude that the rows of this matrix here are linearly dependent of each other, and that's why this matrix is a singular matrix. It cannot be inverted. So the conclusion overall is the rows are linearly dependent, okay, and therefore the matrix has to be singular. All right. Now, as a quick note, here we just saw this defined for matrices of dimension 2, but we can easily extend this definition to other dimensions, for example, to 3-dimensional matrices. Let's do that maybe. So in that case, we would have to obviously consider 3 rows, row 1, row 2, and row 3. So in that case, we will need another coefficient here. So in analogy, we will now call this coefficient gamma. So once we write this, this will be alpha, beta, gamma, okay? And the overall equation here will now also include another term in this sum, namely the term gamma multiplied with row 3. So you'll have to add that, gamma multiplied with row 3. And obviously now the result should be also 3-dimensional, so 0, 0, 0. And then, of course, the last thing here also is that row 3 also has to be considered. But once we've done this, we are basically also ready to do the same, to apply the same logic to three-dimensional matrices. And we can just in the same way check if the rows are linearly independent or not. Here's one further thought about the inverse in general. In a way, you can think of the inverse as a sort of division, but for matrices. Let me show you what I mean. So if we have an equation that just contains matrices, an equation like A times B is equal to C, where this AB is like matrix multiplication, and all of these are matrices, then we can transform this equation into something where we have only A on one side and everything else on the other side. And the way we can do this is using the logic of the inverse. So if we append on both sides the inverse of B, like B inverse, and here also B inverse, then we can use the inverse law, which states that if we have something times its inverse, this thing becomes just the identity, and the brackets don't matter here. So I could have brackets like this, but also this will always be equal to, just like for numbers, to the result of bracketing this way, okay? So that's totally equivalent. And if I now take the inverse of B, and to the left of it I have the original B, then this together, B times B inverse, will be the identity. So I can write A times the identity matrix is equal to C times B inverse. And if I have something times the identity matrix, I can also just restate it without the identity matrix multiplied, because that doesn't change the result anyway. So A times the identity is just A. So I can finally express A as C times the inverse of B, okay? And so this is the idea that just as with numbers, when I have something like AB is equal to C, I can then express A as C divided by B. Here I do the same thing, only the matrix version of it. So I have two matrices A, B, which equal multiplied a new matrix C. And using the inverse, which is basically a sort of division for matrices, I can now express the same relationship, but in terms of A. So I have just A is equal to something, in that case C times the inverse of B. In the three-dimensional case, I have to be a little more precise here, I just realized, in that when I say there are no alpha, beta, gamma unequal to 0, I actually mean that there are no alpha, beta, and gamma of which at least one is not equal to 0. Okay, it's a subtle clarification, but we'll see why this matters when we come to the next and last concept for today, which is the rank of a matrix. All right, so the rank of a matrix is a number, and it basically describes the number of rows that this matrix has, which are in fact linearly independent of each other. All right, and this concept starts to make sense maybe at least 3 dimensions. So bear with me for a moment, and we're going to see an example. So let's say we have the matrix 1, 1, 1, 1, 2, 3, and 2, 4, 6. Okay, that are the rows. It's a 3 by 3 matrix. And now let me also label those rows. So this is row 1, this is row 2, and this is row 3, right? And if we start looking at the first 2 rows only, and we were to just ask, can we find a linear combination, meaning an equation like this, which goes like alpha times row 1 plus beta times row 2 is equal to 0, 0, where not both of alpha and beta are 0, then we really can't find any alpha and beta values which make this true, okay? But as we go and include the third row, namely the row, this one here, 2, 4, 6, then we suddenly can find a combination of alpha, beta, and gamma, where at least one is not 0, namely the combination alpha, beta, and gamma, where gamma is -1, beta is 2, and alpha is 0. Okay, that's why I made this specification here. We are allowed to have 1, 0 in there, but they can't all be 0. Now the point is, when I do this on this full equation for the 3 dimensions, I will get a solution which will give me the desired 0, 0, 0 value. So if I do this, then I'll see that in fact, okay, I have 0 times row 1, so 0 times 1, 1, 1 obviously stays 0, and then plus 2 times row 2, which will be 2 times 1, 2, 3, and then -1 times 2, 4, 6. And you can just compute this and you will see that this is also equal to 0, 0, 0. So the fact that we could find a combination of alpha, beta, and gamma values, where not all of them are 0, which will give us the result 0, 0, 0 here, means that this matrix overall is, as we just discussed, a singular matrix, meaning that we cannot invert it. So it's a singular matrix because when we look at all of its rows overall, we see that we find some linear dependence there. In this case, the row 2 and row 3 are the critical ones because they are, you can see it intuitively by the fact that row 3 is actually a multiple of row 2, right? And if you see this should raise like a red flag and you can immediately tell that a matrix is singular, in that at least some pair of rows that it has are actually linearly dependent. But it's not as bad as, for example, if we see another matrix which goes like this. So, sorry, wrong pencil again. So let's say we have a matrix which has also the rows 2, 4, 6, 1, 2, 3, but also the row -1, -2, -3. Now here you can see that even if we had just looked at the very first 2 rows, like row 1 and row 2, we would already have found a linear dependence, because we can see that the first row is just a multiple of the second row, like there's a factor of -1. If we take -1 times row 1, we get row 2 and vice versa. And also we have the same linear dependence between the second row and the third row, and thus by extension also between the third row and the first row. So in a way, this one, even though both are singular matrices, this one is even worse than that one, in the sense that here all of 3 of the rows are linearly dependent. Like you can't find a pair of rows here which is not. Whereas here, if you just look at row 1 and row 2 together, or if you just look at row 1 or row 3 together, you still have at least 2 linearly independent rows, okay? And that is basically what the rank of a matrix describes. So we would say that the rank of this matrix, so this matrix over here, this is just of rank 1, meaning that there is only one row at maximum that you can consider in isolation, which is linearly independent. Like one single row is always linearly independent by itself. But once you add another row, you will always find a linear dependence. So you can't have any 2 rows which are linearly independent. And this matrix is a little bit better. It's still a singular matrix, but it has rank 2, meaning that we can pick out a pair of, well, 2 rows, which just considered together, those 2 rows in isolation, like together in isolation, without the third row, we can find that they are linearly independent. And so that's why this matrix has rank 2. And Obviously, if we have a matrix which is non-singular, meaning that it's invertible, this one will always have the rank as the number of its dimensions. So if we have the matrix, let's say 1, 2, 3, 1, 1, 1, and now 0, 5, 4, okay? We should not be able to find any linearly dependent rows here, meaning that this matrix has rank 3, and that is totally expectable because this is, as I said, a non-singular, invertible matrix, okay? Now, finding the rank of a matrix is relatively easy in R because there is also an inbuilt function that can quickly tell us the rank of a matrix. So let us quickly see how we can compute the rank of a matrix in R using such a function. All right, so we are back in R, and let's see if we can recover the rank of these particular matrices using the inbuilt function rank a matrix. First, in order to be able to use that function, we have to load a library, which is called matrix. Once that's done, we are ready to roll. So let's maybe first consider this one. We'll define this matrix and call it A. It has which entries? So it has the entries going column by column, as always, -1, -1, 1, 2, -2, 2, 4, and -3, 3, 6. And we shouldn't forget to define the dimensions, which are 3 by 3. So we can define this matrix. We can see it here. Indeed, it's just as what we had written down by hand over there. And now we can do rank matrix, apply this to A, and take the first index from this operation. Kind of an odd thing to do, but again, this is like an object which is nested, and we have to take the first element of this nested object, which is really just the number which represents the rank, okay? So we always have to do this index 1 thing over here. So anyway, we can compute this, and indeed we see, as we had also seen by hand, that this is rank 1, because really all of the rows, you can pick any 2 rows out of this, and they will always be multiples of each other. So that's why the rank is 1. There is only at most one linearly independent row that you can have at once. Once you have 2 rows, they are always linearly dependent. Now let's look at this one. So we can again define this as, so B, let's call it B maybe, which is a matrix again of dimensions 3 by 3. And we'll have to plug in those values. So 1, 1, 2, 1, 1, 2, 1, 2, 4, and 1, 3, 6. Sanity check, indeed that looks quite the same as what we had written here. And we can also do rank matrix of B, and this gives us 2, just as we had expected. And lastly, let's look at this non-singular matrix, which would always have the full rank. And full rank means if it's a 3-dimensional matrix, it should have rank 3, okay? The full rank for 2-dimensional matrices would be 2, of course. So let's do this. So let's call this matrix C. Again, we define it using the matrix command, specify its dimensions, and now go column by column. So 1, 1, 0, 1, 2, 5, and we also have 1, 3, 4. Sanity check. Yep, that looks very much like our matrix over here. And so if we do rank matrix of C, we can see indeed that our rank is 3 as expected, because that is a non-singular matrix, meaning it can be inverted. All of its rows together are still linearly independent. All right, this concludes our lecture on matrices for today. So in summary, we saw what a matrix is essentially and what kind of basic mathematical operations like addition, subtraction we can apply on a matrix, but we also saw the somewhat more tricky or less obvious operation of matrix multiplication and how to tackle that using some ideas we know maybe from how to compute dot products between vectors. We also saw scalar multiplication, which again is rather easy. And finally, we got to talk about also things like the transpose of a matrix, the inverse of a matrix, and also what it means for a matrix to be singular, meaning non-invertible, or to be non-singular, meaning invertible, and how this relates to the concept of the linear independence or dependence of its rows. Lastly, we also saw the concept of the rank of a matrix, which is basically the number of rows that are linearly independent in that matrix. All right, so with all this in mind, I think you are ready to tackle some of the more advanced ideas in linear modeling theory, which will often rely on the so-called matrix formulation of the linear model. So see you guys next week.